Okay, so this is a new trend. This is ionization energy. This is something completely different than atomic radius. The definition of ionization energy, if you're reading this, it's the energy to make something into an ion. That makes sense, right? Specifically to remove one electron. And when you remove an electron, it becomes a cation, it becomes positive, okay? It always requires energy to remove an electron. It's like breaking an electron off. In order to break it off, you have to actually put in energy, you have to pull it off, okay? So it requires energy. This is an endothermic process. The way that we write the generic equation for ionization energy is like this. X is any element plus the ionization energy. This is endothermic. It requires this energy, produces my new element that is charged, and it lost an electron. This is a visual representation of what's happening. I put that amount of energy in, I break that electron off, and I'm left with a positive cation. Real example, I've got sodium here. If you have sodium, if I add in 496 kilojoules of energy for 1 mole of this, I end up with Na plus and an electron. So I have made it into Na plus. So it requires this much energy to remove an electron. Now that's ionization energy. The second ionization energy would be the energy required to remove a second electron. Third, a third, fourth, fourth, and so on and so forth. Okay, so the second ionization energy looks like this. I already have lost one. I have to put in a specific amount of energy. Notice in this case, it's a lot more energy. It's about 10 times more energy, 4,562 kilojoules. I put in that much energy. I can remove a second electron. I have the electron right here. And if it's sodium, for example, I went from Na plus to Na2 plus. Now, Na2 plus is not very natural, right? Na is in column 1. It likes to lose 1 electron and be Na plus. It does not like to be Na2 plus, because when you remove that second electron, you're actually removing an electron from a full energy shell. And we don't want to do that. Okay, that is very difficult to do, which is why this requires so much more energy. Okay, so that's ionization energy versus second versus third and so on. Now we're just going to talk about first ionization energy. Okay, the energy required to remove 1 electron. And this is what the periodic table looks like. Now looking at the general trend, you should be able to see that for each row, it goes up and to the right. So it becomes more difficult. It requires more energy to remove an electron up and to the right. Sorry about that. There are a few exceptions. If you're looking at these rows, like helium requires the most energy to remove an electron. But actually, we've got a couple of exceptions. So for example, I've got this beryllium to boron one. Notice boron is actually lower than beryllium, and oxygen is actually lower than nitrogen. So there are some exceptions, and you do actually need to know those exceptions. So I'll talk about why they occur in just a moment. But across a period, so from the left to the right, it increases. It requires more energy. And down a group, so going from top to bottom, it decreases. It requires less energy to remove an electron. So this is exactly opposite of atomic radius, okay, except for the exceptions that, like I said, I'm going to talk about. So atomic radius goes down to the left, and this is the ionization energy goes up into the right. They're exactly opposite of each other. Now, like I said, you do have to actually know some of the exceptions, and that is there next is does not increase if we're going to the right between columns 2 and 3 and between columns 5 and 6. Now, why is that? Okay. Well, hang on, I'll talk about the exception in a minute. So first of all, I'll talk about why the general trend is up and to the right. And that's for really the same reason that atomic radius is down and to the left. Across a period, I have more protons. All my electrons are in the same energy level. So more protons means it's got more attraction. So it's holding on to those electrons tighter. So it is harder to remove an electron, requires more energy. So like hydrogen versus helium, they both have their electrons in the same energy level. Helium has 2 protons, so it attracts them more. So it is harder to remove one. So there are more protons, which means more Coulombic attractions, which means a higher ionization energy. Going down, down here, same thing. If I go down, those energy shells, right? I add an energy level each time. They get bigger and bigger and bigger. They are further away from the nucleus. They're going to be easier to take an electron off, right? A really big atom, it's it's going to be really easy to remove an electron from the outside of that. So francium, the biggest atom supposedly, would be the easiest thing to remove an electron from. It would not require much energy at all. Whereas if you're looking at this column, right, francium versus hydrogen, it is actually really hard to remove an electron from. It has a much higher energy, ionization energy, because it's so tiny. Those electrons are really close to the nucleus. So it really has to do with distance when we're talking about down a group. So to the right is because of the protons, down is because of it getting bigger and those electrons are further from the nucleus. Now, the exceptions, however, the exceptions are just across, they're not down, they're just from left to right, between 2 and 3, and then between 5 and 6, are because of that whole half-filled shell thing. We've talked about this before, and that is that a half-filled shell, like if it's a p orbital that has 1, 2, 3, or sorry, a p subshell that has 3 orbitals in it, if there's 1 electron in each, kind of stable. Whereas if it's an odd number, like if it's 4, so you've got 2 in one and 1 in each of the other ones, this is actually a little bit more stable. This is decently stable. So it's harder to remove an electron. So exceptions in a period are because half-filled shells are more stable than any other numbers, really, except for full. Full is really hard to remove, and those are your noble gases. Half-filled are kind of hard to remove, and then if there are any other ones, then it's just going to follow the general trend. So you do need to know those exceptions. The reason is because of these half-filled energy levels. So like nitrogen, it has a half-filled shell, and then also beryllium has a half-filled shell, and that's why we have those exceptions. Okay, so try example number 5 by yourself. Go ahead and pause it. Okay, so it says arrange the following in order from lowest ionization energy to highest ionization energy. It may include exceptions. So if I want you to remember that there are exceptions, I'm going to tell you. And really, ionization energy is the only one that you need to know the exceptions for. Okay, so I gave you BE, CA, B, and N. Okay, so I'm going to pull up my periodic table again. BE, B, got CA, and I have N. So N, B, and BE are all in the same period, and CA is down here. Okay, so first of all, I know that CA is going to have the lowest ionization energy. It's the most down and to the left. And then if I follow the general trend, then it should go BE, B, and then N. However, BE and B are in columns 2 and 3. Those actually will be switched because of the exception rule. So it should go CA, and then B, and then BE, and then N. So there is an exception there, and you have to keep that in mind. Reason why is because of those shells. This is beryllium's electron configuration, and this is boron's electron configuration. Well, this actually is a full 2s shell, so this one is harder to remove an electron from than this one. That's why there's that exception. Okay, now I'm going to come back to those successive ionization energies, like second ionization energy and third ionization energy. So this is when I'm talking about a specific atom. So sodium, for example, that was the one we used as our example before. Sodium requires a specific amount of energy to remove 1 electron, 496 kilojoules. To remove a second, it takes about 10 times as much energy because that one is actually a core electron that you're trying to remove. So removing valence electrons, decently easy, requires energy, but not as much. Anytime you start removing core electrons, however, it requires an insane amount of energy. When there is a large jump in the amount of ionization energy, that means you're removing a core electron. So if I had this data, I would be like, okay, well, this must mean that sodium has 1 valence electron. Magnesium, because it goes 738, and then 1450, and then 7,730. So this about doubles, and this about times 6s. That must mean that it has 2 valence electrons and 1 core electron. So we can actually tell based on successive ionization energies, wherever that jump is where we go from valence electrons to core electrons. So you can tell how many valence electrons something has. And when you're doing these, if I say something about successive ionization energies, you should look at the electron configurations. So in example number 6, I said, why is it easier to remove the second electron from chlorine than the second electron from sodium? So we're going to look at those electron configurations. This is chlorines, and this is sodiums. They're just their valence electrons is all I drew them for. Chlorine has 7 valence electrons. So taking off all of these valence electrons is a lot easier than removing core electrons. However, sodium only has 1 valence electron. So the second electron that you remove is going to be a core electron and will require a much higher ionization energy. Okay, so that means just keep in mind if I'm talking about an element and successive ionization energies, when you're taking off core electrons, it's going to require 6 to 10 times more energy than the other ionization energies do.